Okay, so we're about to show the two steps involved in an inductive proof, the basis step and the induction step. In the concrete case where your P, the proposition you're trying to prove is true, your P of little n is defined to be the sum of the first n counting numbers, positive integers. In other words, 1 plus 2 plus 3 plus ... plus n. Okay? And you're given a formula for that. It's n over 2 times n plus 1. So we're trying to prove that P of n is equal to this formula. That's the theorem statement. That's what we're trying to prove. Okay? And we'll do it by induction in two steps. Now the first step, remember, from previous session was the so-called basis step, and you have to show that it's true, that formula, P of 1. Right? So we have to show that P of 1 is true. And what does that mean? Well, what is P? It's, by definition, it's the sum. Well, P of n is the sum of the first n. Well, here we've got 1. The first n positive integers. 1 plus 2 plus 3 ... plus n. Okay. Well, when big N is 1, so you've got a 1 here. Well, there's only one number you're summing, right? It's just 1. so this is just 1. That's what we should get. Right? Now let's see if the formula that we have for P also gives us 1. Now what is the formula? Well, the formula is this. So plug in big N is 1, so that will give you 1 over 2, in other words here. So for when big N is 1, we're just summing one positive integer, the first one, which is 1. Okay. So big N is 1, so you get 1 over 2. And that's 1, so it's 1 plus 1. So that's 2 over 2, well that's 1. Okay. So the formula gives us the same answer as what we got from the definition. So in other words, the formula is true. We know it's true because we can check it against the definition. We know that's true, right? So we know it's true for n is 1. This formula here we know is true when big N is 1. So we've proved now the first step, the basis step. We know that that's been done. That's been proven. Okay, now the second step, so the induction step as it's called, you assume that the formula, this Pn here, is true for when n is, let's say, m, some random positive integer. Okay? That assumption, assuming that that's true for n as m, that assumption is called the induction hypothesis. It's a hypothesis. Right? You're assuming it's true. But if it's true, then you have to show that P of n plus 1 is true. Okay? That's your second step. So your second step is, if this is true, then this is true. In other words, if the formula when n is little m, if that's true, then the formula when n is n plus 1 will be true. Okay? We have to show, we'll assume this, and we have to show that that is true. And true means in this case you put in n plus 1 for n here. Okay? So okay, right. So let's do it concretely now with the actual math. Okay. So the induction step, second step, we'll assume that this P of m is true. In other words, the formula for this is true. In other words, P of m equals this. Right? So instead of big N here in the formula, we'll have little n. So we're assuming that that's true. And that's a hypothesis, right? That's your induction hypothesis. Okay, so we have this formula for P of n. Now we have to show, given this, assuming that's true, we have to show that P of n plus 1 is true. Now what does that mean? It means that you're putting this n plus 1 here for n and getting a result that is equal to this. But how do you know what this is? How can you independently, there's got to be two ways to show. Well, how do you prove that this is true? Right? Well, this way. Right? P of n plus 1 is obviously P of n plus n plus 1. Right? Is that sort of, because what is this by definition? It's the sum of the first m positive integers. Well, you're just adding one more to get this. This is the sum of the first m plus 1 positive integers. Well, obviously that's equal to the sum of the first m positive integers plus the next one. Well, what is the next one? Well, just n plus 1. Right? Okay? So we know that that's true. So we can calculate this, but let's concentrate on this for a start first. When we calculate this, we'll get some answer, but how do we know that answer is true? Right? Well, we'll compare it with the left-hand side. But what is the left-hand side? Well, to show that this is true, we have to show that when big N here is n plus 1, the formula for it is the answer you get to this. What I've just said is critical. Okay? Alright? Now, what is this according to the formula? Well, instead of n, you put n plus 1. So you'll get n plus 1 over 2, that's here, n plus 1, so n plus 2. So this is the formula you should get for this, right? That's what we hope to show is true. Okay? So we want to show that this, in other words this, according to the formula, will be equal to this. Right? Now, assuming that's true, then we know what this answer should be. So if what we get, when we calculate this, if that equals this, then this formula, the formula, when you put n plus 1 here, that formula should be true. Alright, so let's actually do it. So we know this should be this plus n plus 1. We're assuming from the induction hypothesis, the induction step, that P of m is, the formula for it is true. So plug that into here. Right? So therefore P of n plus 1 is this, in other words this, plus n plus 1. So it's this, here it is here, plus n plus 1. Now you've got n plus 1 in common, take it outside, and then inside the bracket you'll have m over 2 plus 1. And you can rewrite that, take the 2 under here, so n plus 1 over 2, and m plus 2. And this is equal to this. Right? So you've done it. So in other words, so we've shown that if P of m is true, then P of n plus 1 is true. Okay? We just showed it. We calculated that if P of m is true,